Hello, in this lesson, we're gonna talk about statement, if statement, and notation once again, as we are getting into another part of this mathematics, okay? We have just covered all of the functions, and we understand that a function is a rule, right? And this rule assigns every input exactly one output. Notation-wise, when we see this notation, right? This notation, right? That's what we see in terms of function, because in this notation, right? We see the input, right? The input is X, right? So that's the input. And that's the input. Okay, and this whole thing is output. Okay, the whole of it is output. Okay, the whole of it is output. So this notation itself has the input and output indicated. Okay, we're going to use some examples so we get used to these notations. Okay, so that's the whole of it is output. Okay, so input is specified, and the rule and the output, right? So input, the rule, apply to the input and the output. You see, it's a pretty neat notation. And because the wave function have input and output, so all the questions you could have, okay, all the possible questions we could have is either about input or it's about output. Of course, it could be about the rule. If the rules are given, right? So there are only three possible questions we could have, three kinds of questions we could possibly have. One is that we have a question about input, and we have a question about rule, or we have a question about output. You see, for example, we have worked with function f of x equals to constant, right? We understand what this means. We understand what it means, right? This rule tells us no matter what the input is, the output is always the same number, C, right? And we know the picture, and we know the graph, and we know everything about it, domain and range. Now, suppose if I write this notation, once the rule is spelled out, right? So this is example number 1. Okay, the rule is spelled out. And we say, okay, let's give me the value for f of 3. Okay, f of 3. Suppose we choose c equals to 2 as we used to do. Okay, c equals to 2. Okay, as we used to do. Then f of 3, it's telling us the input is 3. The input is 3. And the output is what? The output is 2. Okay, input is 3, output is 2. Okay, so in that relationship, right? Usually you don't see a lot of these in the textbook written anywhere. I do it because I think it will be helpful, right? Input is 3, right? And output is 2, according to this particular rule. Now, let's look at the graph. This graph is pretty familiar to us, okay? So I'm gonna take that picture, which we have, right? We take this picture. We take this picture with us, right? And from this picture, we can tell with the input given, input 3 is given. So where is 3? Where is 3, right? This is the 3, okay? So let me make the picture just a little bit larger. 3 is here, right? Input is 3. So if we draw a vertical line if we draw a vertical line, okay? If we draw a vertical line when 3 is given, does that remind you of a vertical line test? Does that remind you of vertical line test? For input 3, there should be exactly one output, right? And that one output is at the crossing with the curve of the function, which is this point. Okay, so this point, I'll mark it as 3, 2. 3, 2. I'm gonna put a red dot right there. And so this point, right? When input is 3, okay, so let's recall the process, right? When input is 3, I draw a vertical line, which is x equals to 3. Okay, input is 3, meaning x as input is 3. So I draw x equals to 3. Okay, so I draw x equals to 3. So I'm going to mark it, right? So that is x equals to 3. Okay, vertical line test, right? So what do we expect? We expect exactly one output, and that exactly one output is 2. So now I'm drawing this vertical line, okay? And right here, that's x equals to x equals to 3. So this vertical line is x equals to 3. You see, input is 3, which is input is x equals to 3. We draw the vertical line, x equals to 3, touches the curve at that one point, and that one point crossing, which is indicating that this point is at 3, 2. Okay, 3, 2. So I'm gonna mark that point for you. I hope you guys follow me. Okay, 3, 2, that point. Okay. 3, 2. Three, 2. So when input is given, we draw a vertical line. And the vertical line has exactly one crossing with the graph of the function. And that crossing indicates input, output. Input, output. Okay, so that's what the notation says. That's what the notation says. And the key graphically is a vertical line test. It's a vertical line. We draw a vertical line when input is given. Input is 3, vertical line 3. If I have input equals to, suppose I have input with any other numbers, okay? So I'm gonna take this piece, okay, and put it right here, right? But what if I have another, I draw another vertical line. In other words, if I have, if I give another input, right? And it will be the repeat. It will be repeats of the same process, right? So if input is -1, right? If input is -1 in this case, right? If input is -1, and the input is -1, the output is 2. So it's a vertical line passing in the vertical line x equals to -1, right? So I'm gonna draw a vertical line okay, across the curve. Input is -1. Okay, input is -1. So this point is -1. So I draw x equals to -1. So input is -1. I draw the input x equals to -1. You see the vertical line. It crosses the curve at exactly 1 point. And this 1 point is what? Okay, just like the previous example. Okay, I'm trying to get you guys really understanding these notation and how they're being used. It's very important because you're going to be using these extensively in your future calculus classes. So input is -1, output is 2, right? So in the similar way, we're going to mark that point. Okay, -1, 2. Okay, this is -5. There, okay. -1, 2, right? At this point, and mark that point, -1, 2. -1, 2, that dot. You see that point? We got that point by, from the given input, -1, we draw the vertical line x equals to -1. Okay, we draw the vertical line x equals to -1. Okay, x equals to -1. Just like what we did with x equals to 3. You see, that's what we do. Okay, so here, right here. There, x equals to -1. I can bring it just a little bit closer to the line. X equals to -1. So that's, let's see, this will be better. Okay, x equals to -1. The negative sign is not so very clear, but that's x equals to -1. And so when input is given, right, we draw a vertical line and the crossing is given as the input and output. When input is -1, we draw a vertical line x equals to -1, which input equals -1, and the crossing is -1, 2, right? Indicating input, output. So this is the common theme of function notation being used, function notations being used, okay? So let's look at another example. Okay, example number 2. So when input is given, right? Because we talk about that function has three pieces. Input is piece, output is input is one category, output is another category. The rule is the third category, right? Or you can say 1, 2, 3, 1, 2, 3. We're given one, following the rule, right? We know the rule and we produce the output. And how do we produce output? When input is given, we just draw a vertical line. From that vertical line, the crossing with the curve gave us the output. Okay, so that's the graphical interpretation. Okay, so let's look at another example. And this other example, we're going to use this function. Equals to x squared. Right? We know very well about this function, right? So I'm going to just borrow that curve here, right? Which we drew, right? So once again, right? With that curve, which is determined by the function, right? Once the input is given, right? It's the same idea. Okay, the same idea. The input is given. And of course, we know the input. The domain, we know the domain, we know the range as well, right? So input and the function, the rule of the function, and it produces the output, right? And that output, in terms of notation, we know the input, output, and the output is the input time itself, the input time itself. So when the input is given, okay, suppose our input, suppose I'm giving you an input, right? Input is, say 2, right? I choose a pretty simple input. And according to the rule, according to this rule, f of 2, the input is given, the output is 2 squared, which is 4. And that will give us the point, 2, 4, 2, 4. And how do we get that point? We first draw the vertical line. Okay, we draw the vertical line because the 2 as the input is given. Okay, so we draw the vertical line. And there's a crossing. At the crossing, there should be exactly 1 crossing. Why? Because it's a function, right? It's a function. For each input, there's exactly 1 output, and that crossing is 2, 4. 2, 4. And that's the crossing. Okay, so hear me. When input is given, we draw, okay, we draw the line. We draw x equals to 2, which input is given. Follow the rule, produces the output of 4. And at the crossing is 2, 4. Okay, so the crossing will tell us exactly what is the input and what is the output. Okay, so input, output. Okay, so here this is going to be 2.2, and this is going to be we just want to make sure we mark the point properly. Okay, 2, 4. 2, 4. And the vertical line x equals to 4, x equals to 2 was drawn. Vertical line. When input is given, we draw vertical line on the curve. That's the point we try to make. When input is given, we draw vertical line across the curve. It meets the curve at exactly 1 point since we're dealing with a function, right? That's the situation from notation graph about how we get from input to output when the rule of the function is given. Okay, so this is one part of the grammar. Okay, then the next question is, what if the output is given? Sometimes the output is given. Okay, and then we're talking about the if statement. The if statement, right? So I'm going to take this piece of the picture. When output is given, right? So we know the output, but we don't know the input. Typically, it comes with the if statement. For example, okay, for a function, take this function, for example, right? This exactly one. This function is a given. Okay? Example number 3. Output is given. Okay? It says if, okay, this piece is equal to 9. What does that mean? It means the output is given. It means the output is given. And how do we interpret this? Well, algebraically, that's how we interpret it. And typically, you're not gonna see this. You're gonna see that. That's the if statement in mathematics. So it ends up to be an equation. It ends up to be an equation. So this is how we get something called equation. Okay, so what in a lot of the cases, output is given. Okay, so we get an equation. Okay, so I'm going to give you some interpretations about this. Okay, before we get into more complicated situations, see how we interpret equation. Okay, so typically we're given something like that, right? They will say solve for x. Solve for x. What does it mean? What does this mean, right? Typically, okay, you probably have seen this before. You probably have seen this before. They will tell you, solve for x, right? And this equation is given to you. This equation is given to you, okay? Very rarely we make that connection between solving this equation and the grammar of mathematics. And this is what we want to talk about. Okay, this is what we want to talk about. All right. So what does this mean? This is solve for x. And I believe most of you can do this algebraically. I have no doubt. You know, some of you can do this. Excuse me. But here, I not only want you to talk about how to do it algebraically, I want you to see the graphical meaning and the interpretation, because only with these thorough understanding, you know what you're doing. We know what you're doing. So what is the meaning of it? What is the meaning of it? Okay, I'm doing this simple example. I'm asking you to be patient with me, because then we're going to look at other examples which have completely similar meaning, but it's a more complicated functions. So we start with a simple function. Okay, the meaning is that when we are told to solve for x, what it means is that it tells us the rule, right, of how to handle that input x. We don't know what it is. Okay, so this basically tells us there's the input, right? And the rule of the function is taking that input and multiply itself. And we don't know what x is, but we know that it's equals to 9. So we don't know the input, we know the output. Okay, so if we do it from the function's perspective, right, we certainly know this function. We know this function. Okay, and this function, which is f of x, wait, okay, arrow, okay, f of x, we know the rule is x squared, x times x, we take the input and time itself, we know the output is 9. We know the output is 9. And we want to find out what would be the input, right? And solving for x means and find me all the possible inputs. Sometimes they're multiple, okay? Find me all the possible inputs such that the output is 9. Okay? find all the possible inputs such that the output is 9. That's what the question is all about. Similar questions are, you have many similar questions. You have many similar questions. That's what we're getting. That's what we're getting into. That's what we're getting into. These are the if statement we're talking about. So in other words, if statements are equations. Equations are if statements. Okay. I want to make that connection because, as I said earlier, in mathematics, there are only 2 kinds of statements. One is a statement, and the other kind is if statements. Statements, usually, it can be expressed in words, and it can be expressed as, it's also called expression, okay? And if statements are equations. So you guys probably have heard about expression, equation. What's the expression, what's the equation, right? Well, expression are typically a statement. If statements are equations. Equations are if statement. And that is always the case. That is always the case. But when an if statement is considered, there's always a function involved. There's always a function. Sometimes it could be more than one function involved. Okay, so I'm saying this, you may not understand this completely. Okay, you may not understand this completely, just take notes. Okay, in the future, you might see that there's one if statement actually corresponds to multiple functions. Okay, in calculus, you're gonna see implicit functions and things of that sort. So I'm talking about those, but we're gonna do one at a time. So once you know what is the if statement and its connection with the equation, and then you can deal with the questions from more perspectives than one. You can deal with the question not only from the algebraic perspective, but also from the graphical perspective, especially in this day and time. It's so easy to get a graph. And we want to make a better use of that graph and understand the graph thoroughly. And you will realize a lot of the questions and the answers actually can be very visual, very visual. That's what I want to get you guys to see. Now, we just explained that, right? So now let me give you that perspective. Since from this question, we understand its connotation, right? And we know the graph, right? Don't we? We know the graph. We know the graph. What is that graph? Right? I'm gonna bring that graph with us, right? The graph we graphed, we're pretty familiar with. We know the output. We know the output. Isn't that wonderful? How do we find output? How do we plot the output? The output is 9. Since we know the output is 9, therefore we're gonna draw a horizontal line, right? Because horizontal line tells us how high, how low. Those are usually the outputs, right? Those are the output. How vertical, those are the inputs, right? We just talk about how to get from input to output. Now we know the output. So we're gonna draw a horizontal line this time. And I'm going to choose a color, horizontal line. When we draw this horizontal line tell us every point on the horizontal line, every single point, okay? Every single point on this horizontal line, what does it tell us? The height. Okay, I wanna give you more visual. the height is 9. All of these green vertical, blue, gray, or vertical line, the height are 9. And where is the crossing with the curve? The crossing with the curve, there are 2 spots. 1 spot here, 1 spot there. These are the 2 spots. Let's mark these 2 spots. The first spot, it tells us is 3, 9. And the next spot is -3, 9. Okay. So what does this tell us? These 2 spots are on the curve. It tells us when the input is -3, the output is +9. Or when the input is +3, the output is also 9. And look at that question we talked about earlier. Find all possible inputs such that the output is 9. So how many possible inputs such that the output is 9? Well, 2 of them, -3 and 3. This is the full meaning realized, right? Because we just discovered when x equals to -3 or x equals to 3, in these cases, right? In either one of the cases, x squared is going to be 9. So the question is solved. Problem is solved. Do you guys see that? So now let's look back what we have done. If input is given, we draw vertical line. The crossing of the crossing with the curve tell us the output, tell us the input and output. When the output is given, we draw horizontal line. Horizontal line, okay? And the crossings tell us where are the inputs such that the output is what is given. I hope that's clear. Okay, algebraically, okay, algebraically, how do we do it? I think most of you know how to do it, right? So this is the graphical rule to identify solutions. But this method of drawing horizontal line when the output is given, this method is absolutely important. We're going to come back to visit and revisit these methods for other functions very soon. Okay, so stay tuned. So let's look at the algebraic way to solve this equation. Okay, I hope you guys have a good understanding of this now. Okay, so now I'm going to move forward to the algebraic methods. Okay, so algebraically, how do we solve this equation? How do we solve this equation? Okay, so solve algebraically. Algebraically, okay? Well, what we do is that we take square root on both sides. We take square root on both sides. Okay, and then the left-hand side, whoops. The left-hand side, what should left-hand side be equals to? We know the right-hand side, square root 9 is 3. What is on the left-hand side? Well, on the left-hand side, if your answer is x, you are wrong. Okay, we talked about this, didn't we? Okay, we talked about this. Okay, so let me remind you of the square root of x squared is what? is absolute value of X. Yes, okay, don't you make that mistake, okay? That mistake can be caught very easily, okay? So the absolute value of X equals to 3. Okay, now we come to this equation, and it's basically if statement. Okay, so when we solve the equation algebraically, it's a sequence of if statement. Okay, it's a sequence of if statement. So let me write down the full meanings of this whole thing. Okay, so starting from here, okay, the way to read it, how to read it. Okay, it says if x squared equals to 9. Okay, then we say then this guy. Okay, and if this is true, right, then the absolute value of X equals 3. So this paragraph, okay, should be read. We should read it as if then, if then, if then. So if then, if then. Do you follow me? So all the if statements should be read if then, if then, if then. Why we insist on reading it this way? Because they are logically connected. There should be no gap in between. So it guide our thinking process. It guiding our thinking process. Okay, so don't just go through like an autopilot. In your mind, if then it should be logically then. Okay, if logically then, if logically then. So the then must be the natural consequence of the if. Okay, if there's any gap there, then your step will be judged incorrect and you're gonna lose point. Okay, for example, I will give you the mistake, the example, right? Suppose that in this step you write X, right? You have made a mistake right there. Because you're telling the reader the square root of X, square root of X squared equals to X, and that is wrong, right? So you can write down your if then, if then, if then you have made a mistake. Okay, so we must correct that kind of mistake. Okay, so this is where the mistake is. So from this step to the next step is wrong. So what will be the correct? What will be correct? Of course, here need to be absolute value, right? So it's very important that the if should lead you to the then logically correct. Excuse me. All right, so when you read it, if then, if then, if then is in your mind consistently. So these are the cases when the if statement. So now we get to this point. Right? And we still haven't found what x's are. So we can use that graph. Do we know the graph for absolute value of X? Yes, we do. We did that, didn't we? Right here. And how do we solve that equation? How do we solve that equation? Well, we see this as a function, the absolute value function, right? We see this as absolute value function, and we know the output. The rule of the function is absolute value. Take absolute value of the input, and we know the output is 3. So what do we do graphically to solve the equation? That's right. We're going to draw a horizontal line again, right? We're going to draw that horizontal line. You can see this methodology is consistent. And there's two crossings. And these two crossings tell us what? What do these two crossings tell us? Each one of these crossings, there's a -3, 3, right? And there's another point, which is 3, 3. It tells us what? When the input is -3, the output is 3. When the input is 3, output is 3. So we have two solutions. We have two solutions. So the solution would be what? So the solution would be either -3 or +3. Not and, because X can only assume one value at a time. So let's summarize. Let's summarize. And you will say, how do I show my work? You've done so much, this and that. How do I show my work to show my understanding about all of these? So here I'm going to show you how to do it algebraically, correctly, and completely to your professor's satisfaction and without too much hustle, okay? So we have shown you part of the work, okay, algebraically. Okay, and the next step, you can just write X equals to +3 or -3. So this will be more like what you've seen before, right? But in the process, I want you to mentally have some connections to the function we have learned before, right? And all of these is if statements. So for example, how do you read this, right? So now let me show you how to read this. This is how you read this. The first sentence, you read it at if x squared is 9, then the square root of x squared is 3. And if the square root of x squared is 3, then the absolute value of x is 3. And then if the absolute value of x is 3, then x is +3 or -3. That's how we read it. So I'm going to put those sentences behind it. Okay. Reads if x squared is 9. Okay. And then okay, be patient with me. I want you to write this down, okay? Because we're going to apply this way of reading to a lot of other applications, okay? So reads as, and then, right? The square root of x squared is that, okay? If then, okay? And then you go ahead to, because they're on the same line, right? You say if right? And then if this is true, then what? Then the absolute value of x equals to 3. Okay. And then there's the next if. If you can see a lot of those repeats are being omitted. Okay. So if, right? Let me try to keep it consistent, right? And then, okay, we read it as then x equals to +3 or -3. So these will be the way of writing, of reading it. So even though when we write mathematics, when we write mathematics, we don't write them this way, but we mentally need to read it this way because we want to make sure every step next is the logical consequence of the previous. Okay, it must be logically connected, linked that way. Okay, so we're gonna do another example. Okay, let's do another example. Here, as an introduction to this if statement equation connection, I would like to give you a variety of examples. Okay, for example, we have talked about all of those basic functions, right? X squared is one of them. X squared is one of them, right? In our first set. The next one, I'm going to, let's see, this is going to be example number 4. Right, example number 4, say they will tell you, solve for absolute value of X equals to 2. Okay. What kind of statement is this? All the solving for, they're all if statement. They're all if statement. They're all connected with a function, right? And what is this function about? Well, this is basically telling us, right? The function, the rule of the function is taking the input, it takes the absolute value of the input, it produces an output, and the output is 2. And tell me, and solving for meaning find all possible values for X, okay, such that the input, such as the output is 2. That's it, right? And of course, we know the output, we're looking for input. We're looking for input. Well, this is related to absolute value function. This is related to absolute value, right? So there are multiple ways to solve this equation. I want to expose you to all these different methods. Okay, we're going to be exposed to all these different methods. One of the methods, right, method number 1, is from the absolute value perspective. So if this is true, right, if this is true, and we still use a graph, right? We still use a graph. We just use a graph. So I'm going to borrow that graph, and this time, we know the output is 2, so I'm drawing the horizontal line 2. Okay, I'm drawing the horizontal line 2, y equals to 2. And there's 2 crossings. There are 2 crossings, right? And from the 2 crossing, I know there's 2 points on the curve. And one of them tell me, one of the points tell me the input is -2, the output is 2. And the other point tell me when the input is 2, the output is 2. Therefore, we have 2 solutions, 2 values for X such that the output is 2. Okay, so the solution then is X equals to what? +2 or -2. So when you see this, you read it as plus or -2, 2 or -2. Okay, that's how you read it. This is the first method. Okay, and there's another method. Okay, the other method is probably more more likely you have seen that before. Method number 2. Method number 2 is that we go by the definition of absolute value. And so we just deal with number line. And So let's look at the number line. Okay, so I'm going to draw the number line. Okay, so I'm going to use this thing and I create a number line. Okay, so this is going to be there you go. And I'm going to just remove a bunch of things. Okay. So this is my number line. This is my number line. So I'm doing it this way because if I use sometimes I use the two different software, they don't talk to each other, right? So this way we can get to the, yeah, this is better. I wish I can remove this Y here, but I cannot, so just ignore it, right? So by the definition of absolute value, right, because we're solving for X, right? We're solving for X. So the absolute value of a number, we don't know to origin, right? So the absolute value of X means the distance between number X and 0 is 2. That's what it means. The distance between number X and 0 is 2. We don't know X, but we know 0. So what's the distance? So I'm going to mark the 0, okay? So I'm going to mark the 0, okay, with a dot, with a red dot. So we don't know what is X, but we know 0. So the distance between X and 0 is 2. So we're gonna measure from 0, right? We'll measure, oh, this is 2, right? So this is 2. And we measure in the other direction, oh, that distance is 2 as well, right? So the absolute value of -2 is 2. The absolute value of 2 is also 2. So from this regard, right? So we get that 2 numbers. Okay, so we get that 2 numbers. That distance, right? That distance is 2. So that there are 2 solutions. There are 2 solutions. And when X equals to -2, right? The absolute value of -2 is 2. The absolute value of 2 is 2. So from that perspective, we very quickly draw the conclusion. So our solution will be these 2 numbers, 2 dots. Right there. So that's our solution because the distance between 2 to 0 is 2. The distance between -2 to 0 is also 2. So as a result, our solution is +2 or -2. Okay, so this is the second method. The second method is from the distance, so from the definition of absolute value, we just use number line instead of using the graph. Okay, so these are the 2 typical methods. I believe the second method was more commonly taught. The first one may not have been taught as commonly. okay? But this is from the function perspective. This is from the function perspective, okay? So let's look at some other examples. Example number, this should be 5, right? Example number 5. Okay, so we've done some examples in our first set of 8 functions, right? We're not going to do them all. So let's look at some exponential functions, right? For example, if I give you say solve, right? 2 to the power of x equals to 4. That's pretty easy, right? I think that's too easy. That's too easy. But we start from easy, okay? We start from easy. I'll give you a next one, okay? I will give you a bit harder one just a little later. Well, for some of you, this is easy, too easy, right? You can tell the answer. So algebraically, so let me give you some methods. You see, we talk about these methods, right? We talk about these methods. Then you say, oh, this is, well, we can use this very easy. But the reason we want to introduce these methods is because some of the methods could solve some questions that may not be easily done, right? So for example, what if I give you 2 to the power x equals to 5, right? Can you give me the answer, right? So we do 2 to the power x equals to 4 in order to, we want to explore these different methods so we can solve any question for any given input, for any given output, right? So first of all, we understand this is an if statement. This is an if statement. What does it say? This is an if statement, right? This if statement basically says, well, if there's an input, we don't know what the input, right? We're asking, we solve for x, right? Solve for x, that's a typical question, right? We don't know what the input, but we know the rule of the function. We know the rule of the function, okay? What is the rule of function? Well, we take that input, we power 2. So that output is 2 to the power x. So whatever input you give me, I'm going to take that input and power 2, and I know the output. I know the output. I know the output. So solving for, right? Knowing the output. So this basically says if the output is 4, and this is the rule of function, and the output is 4, give me all the possible inputs. Give me all the possible inputs. Right? And what are those? What are those? So the first method, right? We're going to use our function, right? Because after all, we've done those functions, right? So did we do the curve f of x equals to 2 to the power x? We certainly did. I'm going to go there, right? I'm going to go there. We did those graphs. We know the domain and range, right? So this is my 2 to the power x. And the output is 4. We're going to draw a horizontal line. We're going to draw a horizontal line. Yes, we're going to draw a horizontal line. And that horizontal line has a crossing. And that crossing on the curve tells us what input produces that output for. And this question is rather obvious, right? So this point is x when input is 2, the output is 4. Yay. Horizontal line. Do you see the consistency in method when the output is given? That's exactly what I want you to see. The rule of the functions can be different, but all the questions we're dealing with is either about input or about output, or sometimes about the rule itself. In most of the situation we're dealing with now, typically in these cases, the rules are given. We know the rule. So we're just dealing with either the input or output. Before this week, right, in the previous week, most of the time we were dealing with given input. So now we're dealing with primarily given output. Does that make sense? I hope that makes sense. So all of your questions is either about given input, find output, or given output to find input. That's all you do. That's all we do all day long. I hope that has become more and more clear to you. The only thing that may be different is the rules are different. If the rules are different, the domain range are different, the involved issues may be different because the rules are different, okay? So in this case, you can see in the first method, right, graphical method, they tell us that. They tell us that, right? 2, 4. So the solution using the first method, right? We're gonna get x equals to 2 right there, right? So from 2 to the power of x equals to 4, we're gonna read it as if, right? If 2 to the power x equals to 4, then x equals to 2. Okay, now, with the second method is more algebraic. The second method is more algebraic. So let's look at the second method. The second method, right? Well, 4 is equals to 2 squared. 4 equals to 2 squared. The second method, well, you probably will go very quickly. Hey, 2 to the power x equals 2 squared, therefore x equals to 2. Well, this can be done only when the function is monotone. Monotone, which happen to be true here. Why do I say monotone? You probably have never heard the word monotone. Monotone means is either increasing function or decreasing function. So if a function is increasing, it's monotone. If a function is decreasing, it's a monotone. But if a function is increasing and decreasing, it is not a monotone, right? So that's why we say a monotone function is a function that's either increasing or decreasing. So let me write it down. This can only be done if the function is monotone. Okay, so now we're going to talk about what is a monotone function. Okay, if a function is either increasing or decreasing, then it is a monotone. Monotone. It is a monotone. Okay, I'll try to keep it in one line. Okay, is 2 to the power x an increasing function? The answer is yes, it's an increasing function. Okay, it's an increasing function. All right. So why we say this has to be only it's a monotone function? Because what's involved here is not just simply, oh, you just go from here, you just equate x equals to 2. It's not that simple. The reason for that step, the reason for this step, okay, is 2 to the power x is an increasing function. Okay. And it is also one-to-one function. You can also quote it's one-to-one function because the increasing function is a one-to-one function, right? Or if you quote this one-to-one function, it also works well. Okay, you can say it's a one-to-one function. Let's use one-to-one. Then you say, what does this have anything to do with one-to-one function? Yes, it does. It's very, very important because I'm going to give you a contrary example. You cannot do this if a function is not one-to-one. Okay, I will give you an example in a minute. Okay, I will give you an example in a minute. Why? Okay, if you look at x as input and 2 as input, right? We're dealing with the function 2 to the power x, right? So this is for input x, output is 2 to the power x. For input 2, output is 2 to the power 2. When the input are the same, okay, one-to-one function means what? For different input, there are different output. And what's the opposite of that? Right? We know what's the opposite of it, right? The opposite of one-to-one is saying what? For some different input, they have the same output, right? Now, since this is a one-to-one function, so for different input, they have different output. For the same input, they have the same output. Let me say it again. For the same output, they're the same input. So these are the same output. Okay, this is the same output. So I want to put all these reasons here because we're going to do a comparative example. We're going to do a comparative example, right? So now the function we consider at hand is x is 2 to the power x. The function at hand is 2 to the power x, right? So when x equals to 2, is a 2 to the power 2. And what does this tell us? It tells us the output are the same. These two have the same output. Do you follow me? For the same rule. Since it is a one-to-one function, if they have the same output, their input must be the same. Otherwise, it's not one-to-one, right? Yes? One-to-one function says different input, we must have different output. Now we have the same input and we must have the same output. You see, that's the one-to-one function applied here. Now, I just said you cannot do this always, right? So let me give you an example. So we did 2 methods. Are there other methods? We're going to talk about other methods in the future. But now I want to tell you sometimes, okay, sometimes you cannot do this. You cannot do this. Okay, so where's my, wait. We did 2 to the power x right there, right? So let's do example number 5. Example number 5, or example number 6. Okay, before we do example number 6, right? Remember, I want to explain to you, you can only do this, right? The output are the same, therefore the input must be the same. You can only do this, the function is a monotone. I've been repeating myself very much on this because this is a very important, it needs to be emphasized very much. For example, note, I'm going to put it as note, sine of x equals to sine of y. Okay, so let me use a capital A and capital B. If sine of A is equals to sine of B, okay, I'm making an if statement. Could I say A equals to B? Is this statement correct? Is this if statement correct? In other words, we have this rule of function, right? The rule is sine. The rule is sine. Okay, suppose A input, right? And B is the input. Okay, so what do we know? So what do we know here? Okay, what do we know here is that we know the sine ratio and the cosine and sine ratio for A and B are the same. Can we say A is the same as B? So in other words, is this true or false? If true, always true. False, once false. If you think it's true, you need to demonstrate it is true. If you think it's false, you just need to give one counter example because false, once false, right? So tell me, is this true or false? Okay, you can pause the recording right now and think about it. Okay, I'm just going to review the answer to you. The statement is completely false. Completely false. Why? Why? So here's why. I can give you a counter example. I'm sure you will have plenty, right? For example, I just need to identify A and B, right? So for example, sine 0 is equal to sine of pi, right? Sine 0 is 0, sine pi is 0. But is 0 equals to pi? Is 0 equals to pi? 0 is not equals to pi. You see, just because the output are the same does not mean the input are the same. Do you see that? That's why for sine function, which is not monotone, we learned that before, sine is going up and down, right, periodically. Well, sine is not monotone. So you cannot use this property we use for example number 5. Okay, so this is a completely false. Okay, so this is a false statement. So just because the output are the same does not mean the input is the same. When output the same, then the input are the same. This is only true when it is 1-to-1 function. Monotone functions are 1-to-1. Okay, if it's increasing, it's 1-to-1. If decreasing, it's 1-to-1. Okay, therefore it's true for increasing, it's true for decreasing. It's not true if the function is not 1-to-1. Okay, so let me give you another example. Okay, let me give you another example. This lesson as an introduction, right? Introduction to if statement in general. I'm going to give you a variety of examples, and then we're going to focus on each category for extended period of time, for longer time. But here our focus is on if statement. For example, solve for x, okay? And the question is, sine of x is equals to 0. So what are the solutions? What are the solutions? What are the solutions? You can pause the recording, okay, and think about it. Well, because we're looking for input, the input are always from the domain, right? The input are always from the domain. So our solution must be in the domain. So I'm going to give you the multiple methods for this solution, okay, for this solution. One method, before we talk about any one method, I want to talk about what's the nature of this question. Of course, this nature of the question is an if statement. This is an if statement again. What is the if statement? What is this if statement about? If statement, okay? It says we don't know the input and we know the rule of the function, okay? And we know the output is 0. And we're gonna identify, okay? We're gonna find all the possible inputs such that the output is 0. That's the nature of the question. That's the nature of the question. So I'm going to give you 2 perspectives, okay? I'm going to give you 2 perspectives. The first perspective is from the definition of sine function. The sine function, okay? So this will relate to ARD. So ARD. So from what we're given, right? We know the output. So we know the D. We know the D because we know the sine ratio is 0. Sine is from the definition, right? Do we still remember the definition? Okay, so let's recall the definition, okay? I'm gonna go there. The ARD, right? The ARD. The A, I will never stop mentioning ARD when trig functions are related. And ARD is our golden key to any question you are going to encounter, okay? Reference angle, definition, reference angle, definition, right? ARD. This is our golden key. So here, where our goal is not to get the answer per se, we want to see how systematic methods are developed. Because you can see all the question we're dealing with is either handling input given or handling output given, right? The rules are typically described, right? So we only have 2 kinds of questions. We've got 2 kinds of questions. So now we're dealing with sine. So I'm going to remove all of these, right? The ratio is y over r. The ratio is y over r. So in our context, right? With the understanding of ARD, and we know that R is always a positive. So for the ratio to be 0, there's only one choice. Y has to be 0. Y has to be 0. Do you guys follow me? Y has to be 0. So if sine of x equals to 0, Y must be 0. And what is that Y? Y must be 0. What happened when Y is 0? Well, your terminal is either this one or that one. Do you follow me? So from definition, your terminal, okay, our terminal, I'm going to use the golden color, right? In order for that sine x equals 0, so the terminal is either this one or that one, right? So what are those angles? Because our question is from D to find A. We're looking for angle because sine x, right? X is following sine, and whatever following sine is angle. So what are those angles? So those angles will be what? It's always measured from standard position. So you terminate here. So how many angles terminates here? 0 is 1, right? 2 pi, 4 pi, 6 pi, and so on and so forth, right? And it could also terminate here, pi, right? 3 pi. So now if we look at all the possible angles that terminate, and they're all measured from the standard position, okay, so I'm gonna bring these two, I'm gonna bring this picture up here. Okay, I'm gonna measure this again. Hold on. I hope you follow my reasoning. Follow my reasoning. Okay, you need to be patient. If you feel tired, feel free to pause and come back, okay? So let me talk about this one more time. We know the output has to be 0, right? Because that's the if statement. If sine x equals 0, right? Of course, this x is different from the x over here, it's the input, okay? And this x is indicating the point. So that means the y, that ratio has to be 0. The blue has to be 0. If the blue is 0, what are the terminals? What are the terminals, okay? So I'm gonna draw the terminal on another picture, right? So this time I'm going to just clean up. I'm going to clean up. Okay, I want you to draw the picture because y must be 0, right? And this is going to be right? So y must be 0. So the blue line is completely, the blue line is gone. Okay, the blue is gone and this whole thing is gone. Okay, so the terminal, so what I'm drawing here are the terminal. Okay, the terminal where the ratio of sine will be 0. Okay, so that's what I'm drawing. So I need to remove one more thing. Delete that, delete that. Okay, I think that should be said. I need to remove the R. I need to remove the R, delete. So this is one of the terminal, okay? So I don't need that. So this is one of the terminal, right? And there's another terminal, there's another terminal. The other terminal will be on the other side. Actually, I don't think I need the, this is the green. I don't think I need the red. Okay, so this is one terminal that will cause the sine ratio equals 0, okay? from the definition. So right now we're doing from D, okay? And we'll try to figure out the terminal. We're trying to figure out the terminal. We're trying to figure out the terminal. I'm going a little slower. Okay, you can go fast forward if you feel I'm just too, explain too much. Or just take a break, Okay, so what I'm going to do, I'm showing this methodology. I'm showing you this methodology. So either the terminal from standard position over here or over there. Okay, in either case, right? So these are the two terminals. Right? That will cause the sign ratio equal to 0, because in those cases, y equals 0, okay? So now we're gonna measure the angles because we're looking for the angles. We're looking for the angles such that sign ratio is 0. How are the angles measured? The angles are measured from standard position. That's the ARDA, okay? So this one, angle when x equals 0, we got what? We got sign ratio equals 0. Again, pi, sine pi is 0. 2 pi, sine 2 pi is 0. Sine 3 pi is 0. Sine 4 pi is 0. 5 pi, 6 pi. All of these sign ratios, again, we get 0, right? So do we have a solution now? Yes, we do. And this process, you see, from a definition, we get to what? We get to A. Okay. Earlier on, I was telling you, all the questions you deal with in trigonometry can be solved by A, R, D. Before this week, before this lesson, most questions we're doing are from A to R and to D, okay? For the arc sine function, we're doing D to A, okay? So the arc function from D to A. And now we're doing D to A again. DRA. Excuse me, DRA. What is an R here? Well, in the arc here, we're trying to identify the terminal, right? We're trying to identify the terminal. Then you say, well, that's not exactly reference angle. That is true. That is true. But R is basically the reference to the terminal in order to find the solution. So this is what we're talking about. Okay, so all the questions you're dealing with in trigonometry is either A to D or D to A. Okay. So now we figure out once we have identified the terminal and we're going to measure the angle from the standard position, and each one will give us the angle. In fact, the solution to this question are going to be what? Right? So if, okay, so I'm going to write it down, formulate what is the solution, right? And how do you show work, right? Sometimes you say, oh, do I have to say all these? Do I have to write all this down because I have said a lot and talked a lot, right? For you to show work, in this case, it's x equals to k times pi, k pi. And k is what? Is any integer, because we just talked about, right? 0 pi, 2 pi, 3 pi, 4 pi, the multiples of pi. So this piece, right? If you talk about shown work, that's all you need to show. That's all you need to show. But you need to understand this much. You need to understand, you need to have that perspective. Why? Because the question could be changed to sine x equals to 1/3. Sine x equals to 1/2. You can do that, right? What if the sine x equals to 10? What if sine x equals to 10? What happens? Think about that. Think about that. Okay. All right. Okay. Wait a second. So this question is solved. This question is solved. So let me give you another example. Right. So you can see ARD is golden. ARD is golden. So you eat all the question you deal with. Okay. So I'm going to put it here. All the question we're dealing with is either A to D, D to A. Okay. All the question we're dealing with, this life of mine or your life related trigonometry is either A to D or D to A. No exception. At least I haven't seen it. I've been to graduate schools. If you've seen one, let me know. I'd like to know. Okay, so let's do another example. What if you say solve for sine and that equals to 10? Oh my God, equals to 10. What will be the solution? Well, before we solve 7, let's look at the second method, right? I just talked about the first method, didn't I? Right? This is the first method. This is the first method. From the ARD's perspective. I haven't told you the second method, right? The second method, I tell you, I assure you, you're gonna love it. I saved the best for last. I saved the best for last in this case. Okay. What if we don't use definition? Right? What if we don't use this definition? We look at the second method. Right? We look at the second method. Right? Remember we talk about multiple methods, right? Well, since we talk about the sine function, right? Since we have this if statement, right? And we know the definition for sure, but we also know the sine curve, don't we? Don't we know the sine curve? Right? We spend so much time graphing sine curve. Why do you think we do that? We graph more points than any textbook have done. I can proudly say that. Right? And it is for this moment right here, right now. Okay, at least this is one of the moments, right? We know sine curve, don't we? Everybody does. Everybody does. We also understand the meaning of sine curve, don't we? We also understand the meaning of sine curve. All right, so I'm going to make some adjustment to the view. Here, right? Okay. When I draw these pictures, okay, I want you to still think about this question, okay? Think about this question because we have so much thought, we have so much thoughts, you know, flush seconds. Now we're still trying to solve this, you know, solve for sine x, okay? We're solving this equation, right? And we know the curve. What does this curve tell us? It tells us the input and output. So now we know the output is 0. We know the output is 0, guys. Remember that horizontal line we draw for the previous questions when we know the output? Yes. Can we do it for sine? Yes. Absolutely. Okay. So that's what we're going to do. We're going to draw a horizontal line. Okay, we are going to draw that horizontal line. I make it broken because I still want you to see the, you know, the x-axis. And this horizontal line touches the curve. And the point, at the point of touching, what are those points? Tell me, what are those points? What are those points? Every point they tell me the same output, don't they? Let's mark these points. Let's mark these points. And what is this point? That's easy, right? 0, 0. Input 0, output 0. Input 0 means the input for sine is 0. Output for sine is 0 because this is a sine curve. Right? How about this point? Pi, comma 0. Sine pi is 0. How about this point? 2 pi, comma 0. And we are to identify all the possible inputs such that the output is 0. So what are our solutions? We just pick up the input, 0, input pi, input 2 pi, and keep going. And there are more, right? So how about this point? That's negative pi, 0. And this point, what would that be? Negative 2 pi, 0. So how many points do we have? How many inputs? What are all the inputs? What are all the inputs such that all possible inputs such that the output is 0? Of course, 0 plus pi minus pi plus 2 pi minus 2 pi and so on and so forth. So multiples of pi. So we draw the same conclusion. But this is more visual, isn't it? This is a more visual. Okay, this is a more visual. Okay. So the solutions are identified. The solutions are identified. So the solution, how do we show work? Right? If sine x equals 0, right? That's how you read it. And x equals to what? K pi. And then you just have to tell the reader k is any integer. That's all the work you have to show. Would it be nice that you show the picture? Sure, but if you do show the picture, you may like to mark the points as well. Okay, and you can see the second method, right? And next, do you think you're ready to solve for sine x equals to 10? Yes, are you? So you may pause or you already know the answer. Unfortunately, when I'm recording this, unfortunately, I would not be able to hear you, but I'm sure you already know the answer. You already know the answer. What is the answer? What is the answer? What is that example? I'm going to bring it back. Example number 7, right? Example number 7. What is the solution? We have the picture right here, right? And think about, right? It's an if statement. If it is still if statement, everything stays the same. And then what you do, if you take that curve and you want to use the same technique, and you're going to graph, right? This time you're going to draw a horizontal line. The horizontal line is y equals to 10. Yes. So let's draw that horizontal line equals to 10. Right? Horizontal line equals to 10. And whoops, we don't even see that line. Why we don't see that line? Well, my view need to be adjusted, right? So I'm going to make sure you get to see that view. Oh my God, what happened? No touch. the horizontal line, no touch to the curve. What does that tell you? No solution. No solution. No touch means no solution. No solution means what? There's no input such that the sign of that input is equals to 10. No input such that the output is 10. That's what it means. So according to this rule of function, okay, according to this rule of function, it's impossible to have any input that produces that desired output. No solution. Well, does this question has to be answered with this way? Of course not. Of course not. So one way you can think about the graph, right? Think about all the time we spend graphing, right? Why do you think I did that? We plotted points more than any textbook have done. Okay, for good reason, because textbook has limited pages. Why? It's to use them. It's to use them. Okay, we do those things in order to apply. And this is the moment of application. Okay, when you look at the output 10, what is the range of sign? Huh? What is the range of sign? Which is on the midterm exam. What is it? Well, for any input x, the output of sign will never be less than -1 or larger than +1. For any real number, x. And of course, it cannot be equals to 10, right? So if you just quote the range of sign is between -1 to 1, then your answer is perfect. Okay, so let me give you another version of saying there's no solution. Okay, so method 2. Okay, of course, this will refer to that one as method 1. Okay, you use a graph, you have a visual. We have a visual to see this, right? And for this one, we can just use the range. Method 2, we can say solving for, okay, I'm just gonna make it complete, okay? For the same question, we say no solution because this is what, because of that, okay? And that's one version, okay? You can also say no solution because the absolute value of x is less than or equals to 1. That will work too. Or no solution because, okay, 10 is outside the range of sign x. So all of these statements can be used to make your case, to make our case. Okay, so let's look at another example. Let's look at another example, okay, for the if statement. Sometimes, okay, sometimes we might have a little bit more complicated situation. We might have a little bit more complicated situation. We have covered the if statement for, you know, as simple as x squared, absolute value of x, right? Exponential, logarithm hasn't been covered. So I'm going to use an example for logarithm. Next, okay, example number 7. Example number 7. Example number 8. Once again, solve for x. Solve for x. So the equation involved is ln x equals to 1. Ln x. Okay, we're going to try to use a lot of ln e to the power x in the future because you're going to need them. You're going to need them a lot. Okay, you're going to need them for calc. Okay, in calculus class, you will most of the time, you're not going to see 2 to the power x, 3 to the power x very much. Okay, you're going to see e to the power x a lot, e to the power 2x a lot. You're going to see e to the power negative x a lot. You're going to see ln in its many forms. So we're going to prepare you for those moments. So now, solve for ln x. What does that mean? Okay, what does that mean? Same thing, right? Well, if it's an if statement, if ln x equals to 1, right? Find all possible values for x such that right? Ln x equals to 1. That's the issue. That's the issue. Okay. So since we emphasize so much, there are more than one method here. So the first method, well, what's ln x? What's ln x? What's ln x? Here's ln x, right? We spent so much time graphing this function, didn't we? Right, so let me make some adjustment of the view. Yeah, okay, so that should be enough. So once again, you can see it's a different rule now, right? We dealt with the rule, we dealt with other rules. Okay, so now sine x, well, I'm sorry, ln x, this is the ln x curve. Input, output. Input is x, right? Input is x. And the rule of the function, right? It's ln x, a different rule. And the output is ln x, right? So now we know the output equals to what? The output is 1. So what do? We're going to draw that horizontal line. Do you see that consistency of drawing horizontal line when the output is given, right? That's what I want you to see, regardless of the rule, regardless of the rule. It doesn't matter what rule is. When you know the output, you draw a horizontal line. That's how we use a graph. Okay. So let's draw that horizontal line there. And where does it cross? It crosses a point. And the point, at the point of crossing, there's an input and there's an output, following the rule. And this point, what is this point? What do you think should be this point? What is the answer? What is the answer? I'm not going to tell you the answer. I'm going to pause just a second, okay? You should pause the video, pause the recording. What is the answer? And come back, okay? So now you already see the answer. You already see the answer. And the answer is that point is what? What is that point? When the input is E, the output is 1, right? Yes? You see that? There. And we want to identify all possible values for X, and that X is what? Is E. Do we have more solutions? The graph tells us we have only one solution, but this function is what? It's increasing function. It's 1 to 1. Okay, it's 1 to 1. Okay, so the first method, right? If ln x equals to 1, right? If ln x equals to 1, then what? Then x equals to E. It's a 1-to-1 function. We talked about it before. We spent all the time graph ln x, didn't we? So if you need to review that part, you should do that, right? We graphed more points, I can proudly say, that any textbook have done. Any textbook has done. Why? Because we want to enhance the idea that all we're dealing with is input given or output given. When input given, vertical. When output given, horizontal. Okay. All right. Method 1. Method 2. Okay, method 2. The second method, of course, there's the second method, of course, is definition. Definition, right? And what is a definition? Do you still remember what is a definition? What is a definition? What is a definition? Do we still remember the definition? All right, so let's review the definition, right? Log base of anything. Well, this is the moment, like we're gonna have specific sessions to review logarithm, okay? Equals to triangle if and only if, right? B raised to the power triangle. Remember, we also talk about domain and range of these issues, right? So this is the moment we get to use it. I encourage you to review those sessions in the previous weeks that we have talked about these graphs, right? Because we spend so much time on trig review. We need to constantly review these things, and you need to make sure it stays with you because you're going to need them a lot in Cal, okay, in calculus classes. So for E, right, for base E, okay, so I'm going to give you a gradual evolving of these formula, right? So when the base is E, okay, so let me make it think out aloud. Okay, review of the definition. When this piece is E, let me put it here, just closer to us, okay? E, the base is E, right? And for E, this is ln, right? Yes. So now we have ln x equals to 1. So in this particular case, we have ln x equals to 1. And when we have the definition here, let's find the correspondence. So omega is x, triangle is 1, right? So triangle is 1. Omega is x. There you go, x is e, because e to the power 1 is e. Thus, the solution is x equals to e. You see, if you use definition, it's also pretty obvious, but it does take practice. It does take practice. Okay, so in summary, what have we done in this lesson? In this lesson, basically, we connect with what we did in the previous lessons. Okay, we emphasize the function concept. Okay, let's go back to the top, right? When the input is given, and we know the rule, okay? All of these provide that we know the rule of the function. When input is given, since we know the rule of function, graph is at our fingertips. When input is given, we draw a vertical, we draw a vertical line, and vertical line crosses the curve. It give us a crossing, and that crossing tell us for that input was the output. Okay, whether you can get the precise value of the output, that's another matter. Okay, so that's why sometimes we get a precise value, sometimes we don't. And that's why we need the algebraic method, because algebraic method sometimes, well, algebraic method in many cases were able to give us the precise value, and precise value we want, especially your math professors. Okay, for academic reasons. Now, if the output is given, what do? We draw a horizontal line, right? So horizontal line tell us that if the output is given, we're looking for input under the if statement. So we know the output and we can identify the input. When we draw that horizontal line across the curve, it will help us to identify all the possible inputs such that they will give us the same output. You can see from the function concept, we have these two systematic methods to deal with them. Are there a lot of algebraic details we need to, and techniques we need to learn? Of course, of course. But all of these is about either input or output. Okay, statement or if statement, okay? So this is the simplicity I wish you to see for whatever you have learned up to this point. And you will continue, and you're gonna use these tools, okay? The multiple methods we learned, and hopefully these multiple methods we learned, will connect us from what you have learned in the past, and will connect you to what you will learn in the future, and to complete your academic journey, So I hope that, and we will continue on this picture, right? This is the big picture. And of course, we're gonna deal with individual rules. Okay? As we're dealing with these individual rules, okay? As we're dealing with these individual rules, and we're gonna have different parts, okay? So we're gonna have different set of questions in our discussion, okay? The first category, and of course is trig questions, trigonometry. The second category is exponential and logarithm. And the third category, of course, What is the third category? The third category would be, you know, absolute value, quadratic, and polynomials, and, you know, quadratic, which is a very typical academic questions, okay? Absolute value functions and the polynomials, right? And square root functions, right? So these are the three major categories we're going to touch, okay? And what we have discussed is about, you know, the output is given, output is a specific number, and input is given, you know, horizontal, vertical. But in another category, which could include all of them, is the inequality. Inequalities for all of these cases. For all of these cases, how do we handle them? How do we apply our function ideas to these inequalities? Okay, what are inequalities? Greater than, larger than, smaller than or less than, equal to. There's all these inequality signs, okay? So when we get to that inequality such as greater than, right? Greater than, equal to, less than, equal to, not equal. How would these have anything to do with function? We're going to talk about those too, right? So we just talk about equal. The output is equal. What if the output is larger? The output is less. Output is greater than equal. The output is less than or equal. Or the output is not equal. You guys hear me? Right? And they're all about input, output. No, I haven't seen much of exceptions, really. I hope these will give you a simpler perspective about the mathematics you are dealing with. Are there complexities? Yes. Okay, so always be ready with your paper pencil very close to you, writing down, try to understand. Well, this lecture is pretty long, and thank you for watching. Until next time.